Hello everyone, this is Sumit Yogi. I am from MCA 6th semester section B, and here I am going to present a PPT presentation on demand paging and virtual memory. Here I will explain the concept of demand paging and virtual memory. This is video for my third assessment, so let's begin it. This is my introduction page, and here we go for our introduction to virtual memory. So first of all, what is virtual memory? So virtual memory is a extended version of RAM. RAM is a storage where the process and the system program runs, but there are some programs in the system which exceed the limits of RAM. So for that programs we use virtual memory. Virtual memory simply converts the physical storage or physical memory into a temporary RAM where we can place our programs data which are not necessary to be presented in the RAM, but they are essential for the progress of the process. So here we have logical addressing, physical memory, and OS managed. So logical address space is a program can use more memory than physical available memory, and physical memory only the required page are load into the runtime. What is it need? So virtual memory allows system to run programs larger than the physical RAM. It benefits in memory efficiency. Only active pages are kept in RAM, free space for other process. Second is large program support. Programs exceeding RAM size can still execute without error, and multi-programming. More process can be loaded. Second is what is demand paging? So demand paging is a method of virtual memory management where the pages of process are loaded into memory only when they are needed. Demand paging works as demand and supply. Its formal definition is a lazy loading technique. It is a lazy loading technique where the OS use page table with valid invalid bits to track which page are in memory. Second, paging basics. So memory is divided into fixed size unit called pages, logical and frames. Each process has separate table mapping page, frame page in RAM. And lazy swapper never swap a page into memory unless it is required. This minimizes unnecessary disk OS, reduce startup time, and valid and invalid bit. Working of demand paging. So a page fault occurs when a process tries to access a page that is not currently in RAM. The OS must then fetch it from the secondary memory and place it into the free. So here the hardware support is needed. Valid invalid bits in the page table, restart instruction capacity, and secondary storage is swap space. So first of all, in working of demand paging, process reference page, CPU generates a logic address and check the page table. Checking page table, if valid bit is equal to 1. So process refers pages, CPU generates a logic address and check the page table. Checking page table, if valid bit is equal to 1, if page is RAM, if invalid page, fault is triggered. Page fault trap, OS take control, locate the page on disk and finds a free frame in RAM. Resume execution, when the page is loaded into the frame page table. Update process, retain the faulting instructions. Next is the need of demand paging. So demand paging solves the critical challenges in modern OS memory management by making memory use far more efficiently. It provides efficient memory use. Only active pages are loaded in the RAM. Faster program start by program being executing immediately without waiting for fully load from disk. Large program support. Program larger than the physical RAM can run using the virtual memory space. Better multi-programming, more space or more virtual memory increase the simultaneously improving CPU through output. Next is page fault handling process. When a page fault occurs, First, it traps to OS hardware detect invalid pad access and generates a trap transfer of control to OS. Save process state. OS saves the state of the fault process for a later restart. Local locate page on disk. OS checks the internal tables to find the required pages location and swap space. Next is performance of demand paging. So when page fault and rate are their impact. So low page fault rate P is equal to equivalent to 0. Most access hit RAM directly. Performance is close to normal memory access time. High page fault, so P is equivalent to 1. Frequency disk access several degree. And thrashing. When page fault rate is extremely high, the OS spends more time handling faults than exiting process is called. Here we can see the page fault rate versus system performance. If the page fault rate percentage is high, then system performance decrease gradually. Effective access time ETA. So ETA, effective access time, counts for the both normal memory access and the expensive cost of page fault, is equal to 1 minus P into M plus P into page fault time, where M is memory access time, P is page fault rate. Memory access time. So typically RAM access time is equal to 200 nanosecond. This is the cost when the RAM requires page is already in memory where no page fault is occurred. Page fault time. When a page fault occurs, the most performance disk typically 8 milliseconds slower than the RAM access. And here is a calculation. Advantages and disadvantages of demand paging. Understanding the trade of demand paging is essential for designing efficient programming. So advantages are less memory usage, only requires pages are loaded, better resource utilization, CPU save productive RAM by running more space, faster process start, process being executed fastly. Disadvantages: page fault overhead. Each page fault involves OS intervention and it is very costly in time. Disk delay. It increases the latency. And our last module is real life example and conclusion. So think of a demand paging like a student using a library. Fetching a book is equal to page fault. When you need a book not on your desk, you walk to the shelf to get it. This increases the delay. Shelf disk swap space. All books are exist on the shelf. Only the one you need right now are on your disk at a time. Conclusion: demand paging is a virtual memory technique that loads page only when needed. A page fault occurs when a reference page is not in RAM, then the OS fetches from disk. Every small fault rate significantly degrades the performance. Benefits of it is low memory usage, faster start, multiprogramming. Here the risk involved are page fault overhead and thrashing. Keeping the page fault rate close to zero as possible is the primary goal of good OS system management. Thank you.